let's recall that as the battery or as the charge carriers leave the battery, what happens is their potential energy remains the same until they hit the light bulb. Then that energy is used up as internal energy to give off light and warm up the filament itself, and that drops off the potential energy of the charge carrier. Then when it's returning to the battery, it's got no potential energy, it's just being pushed forth by the electromagnetic field in the circuit. And then once it reaches the battery again, the battery charges it up by doing work on the charge carrier and giving it potential energy until it gets back to the actual lead, and again we go through this circuit. Now, a schematic diagram is defined as a visual representation of an electric circuit, and you simply use standardized symbols for this. And the idea to standardize things is so that everybody can read them the same way. So this could be some sort of a power source, a random light bulb and a random light bulb, and no matter what the power source is, whether it's a battery, whether it's a generator, and this is a light bulb, it doesn't matter what the wattage is on the light bulb or what the voltage readings are on the battery, but the schematic would look the same. So again, a schematic is just a representation or a model using physics. Next, we'll take a look at some of the components used in a schematic, and first and foremost are wires, because wires connect everything. And since wires really have negligible resistance or no resistance, we can represent them just using a straight line. Now, when a wire is turning, we use a right angle in the diagram, even though a wire is curved, right? And remember that wires are just, copper wires that conduct electricity. Second are resistors, or what are called circuit loads, things that control the current in the circuit. So a resistor itself is able to use up that voltage in a sense. So we think of the fact that it slows it down. So we put a little squiggly line here to show that it's being slowed down. It's taking a slower path suddenly along the wire, and then the current continues through there. Next is a bulb, or a lamp in general. And a bulb is really just a resistor, but we specify that just by putting a circle around it. Okay, so you just put a circle around the resistor, and you could draw it the way it's shown here, or you could simply even draw it like this, with a circle around it. Fourth is a plug, and a plug has two prongs on it, one positive terminal, one negative terminal on the prongs. So we can draw it this way to represent that. This is the positive terminal, this is the negative terminal, or it could be drawn like this. This is one of your more common representation. A battery shows just simply two lines, one line larger than the other though, again showing a positive terminal and a negative terminal. Now some batteries, like computer batteries, like lithium cell batteries, are made with more than one cell. So if there are multiple cells in a battery, then we have to consider the fact that we have to draw those several cells here. So this would be a battery with 3 different cells in it. Finally, the last thing is to take a look at as a switch. And a switch just opens or closes a circuit. And this is an open circuit because the switch is open. This is a closed circuit because the switch is closed. So an open switch would look like this, and a closed switch would look like this. The 2 little circles here are indicating these junction points right here. So these little points here in the junction are those little circles right there. Now an electric circuit is simply a set of electrical components connected to provide one or more complete paths for the movement of the charge. So the charge may go along one path, but there may be several paths to look at, and we'll see that when we get to series and parallel circuits. But what a circuit really consists of, a circuit consists of 2 things at a minimum. It has to have a potential difference. The potential difference is really just the source of energy. Without a potential difference, there's nothing to establish the electric field to cause these charge carriers to move through the circuit. And then second, you need a load-bearing element, something like a light bulb or resistor that can dissipate the energy. So there's all this energy that comes from the potential difference, and if there's nothing here to use up the energy, what will happen is the wire will try to use up the energy. And we'll talk more about that, and we'll talk about something called a short circuit and what happens there. Next, let's take a look at a closed circuit. And what a closed circuit really is a circuit where the electrons can move from one terminal to the other, and a current can exist when the switch is indeed closed. So when we have a circuit and we think about a switch here, so let's say it was just a simple switch that was open. So we've got our potential difference, and we've got our load-bearing element. So this is our basic circuit. Now we introduce a switch. As of right now, what happened is the electrons would want to move through here, but they wouldn't be able to complete the path. So because this path is not completed, there's no EM field that's established. But the minute the switch is closed like this, and this is no longer open now, it's closed, what happens is it completes the path. So the potential difference starts to generate, or it starts to give energy to the charge carriers and pushes them through this circuit here. Now a light bulb, what happens is this. This is really kind of interesting to think about. the current enters the light bulb through the base connection right here. So it takes a look here, it contacts the base, so here's the bulb, right? Here's the bulb itself, this is metal, this is metal. It goes through this wire, it connects to the actual bulb right here. Then it flows through the bulb into the filament. And when it passes through the filament, the energy is converted to thermal energy. And again, this is not all bulbs are this way, right? We know that some are gas bulbs, those incandescents there. And light energy, okay, so thermal and light energy. Then it continues through the circuit. There's no energy in the charge carriers. The charge carriers continue through, they hit the side of the bulb, then they go into the side of the contact in the actual base here. Okay, we're back out the side of the metal socket, and once they travel through the metal socket, they come out the other terminal and back through. And what happens is then those charge carriers re-energize or gain energy from the power source and continue to go through. And it creates a circuit. Now this light bulb is an example of an old school light bulb. Now we see so many light bulbs nowadays that are incandescent that use things like gas and chemical reactions to generate light, and they don't give off heat. So that's why this says thermal energy, not all bulbs, because not all bulbs give off thermal energy or give off heat. Something that we should note here is that if these two wires were to touch, now clearly they're insulated here, right? There's rubber around each of them. But if the two wires were not covered in rubber and they were to touch, what would happen is this. You'd have your power source right here, and it would generate a flow, right? But what if they touched somehow? Like what if the wires got bent and they somehow crossed and then came back? Well, what happened is this. The charge carriers would want to take the path of least resistance, and all this energy in the charge carrier would go like this, and it would come right back through. It wouldn't actually go into the light bulb. So this would create a short, and what happens is the bulb would never get any energy. And without some sort of a load-bearing element, these wires, and I'll highlight them in red, this portion of the wire that crossed would start to heat up, because it would use up all the energy in the charge carriers, and when this heats up, it would start to ignite, and you would have a fire. And what happens there is that causes a lot of melted wires and simple house fires that you have from these short circuits when you have old wires where the wire rubber casing is old and deteriorating. Finally, we'll take a look at the term EMF. An EMF is a source of energy that can cause a current to flow in an electrical circuit. And we've talked about this already, but the idea of an EMF is what I want to discuss now. An EMF is interesting to think about because the terminal voltage is actually slightly less than the voltage supplied by the EMF. And the reason for this is because of this small internal resistance here that's really occurring in the battery. So a battery like this battery, for example, a 9-volt battery. And a 9-volt battery, if you measure with a voltmeter, actually doesn't give off 9 volts. The difference the terminal voltage that it would give off would be like 8.9 volts. And that little difference is because of this small internal resistance. Now, we consider this to be negligible because it's so small. But really what we're saying is that conservation of energy is what leads us to the fact that the potential difference across a load-bearing element is really equal to the terminal voltage. Okay, so the terminal voltage here, the voltage between these two terminals is equal to the voltage across this load-bearing element. Although, again, the EMF provided is really a little bit higher than what this bulb is going to feel because of the small internal resistance.